So again, welcome back to the latest lecture session. Again, we were looking at, I believe, a case study, right, with respect to monitored natural attenuation, and we had a site that was near the river, I believe Mississippi River in Louisiana, right, and we were looking at, let's say, a spill of DNAPL and some LNAPL, and the DNAPL percolated through both the clay and the relatively more hydraulically conductive alluvium layer, right, and we had the relevant aspects, and we had the site characterization looking at complexity of the particular subsurface, right, or had an idea about the complexity of the subsurface, and then we moved on to looking at, let's say, what are the relevant concentrations at the source, and why this particular site might be a good idea or good fit for natural attenuation. And in that context, we saw that it can be a good fit because your relevant reducing agents like ferrous iron and let's say what else now, hydrogen, which are electron donors, are at relatively high or sufficiently high concentrations, while the relevant competing electron acceptors, right, competing electron acceptors to your chlorinated solvents, which are your contaminants. Your contaminants are your chlorinated solvents, which is what you want to degrade, but if you have oxygen and nitrate, nitrite and sulfate, let's say, they are going to act as competing electron acceptors, then your particular contaminant will not be degraded, right. So that is something to keep in mind, and we saw that the concentrations of those competing electron acceptors, let's say, was relatively low, right. And then we moved on to looking at, let's say, data at particular sites, along the flow paths, and we saw that a daughter product or a byproduct of this particular degradation, let's say, was found, which was cis 1,2 DCE, let's say, right. It is more or less with respect to the structure, let's say, right. That was found, let's say, at relatively high concentrations, right, and then in this context we were about to look at, let's say, the bioattenuation screening parameters and scoring. As we can see here, we have different criteria, let's say, based upon which you can evaluate your relevant bioremediation feasibility and so on. So let us look at those aspects. So first we have contaminant or the geochemical indicator here, we are going to look at that, and different criteria out here, and is it present in the NaPl source, yes or no. Why is this relevant? Because let us say some of the byproducts, let us say, if they are not present in the source but were present downstream, which is the case with, let us say, this 1,2 DCE, right, you can say that the biodegradation is taking place, let us say, or that is one of the indicators of biodegradation. So you have at different wells, I believe, right, and also at the deep wells, let us see, right, and again you have a score for each of them and the relevant concentrations there, right, based upon these scores. Let us look at them. So DO, right, you want it to be relatively less, right, it is not available, I guess it will not be present in the NaPl source. In the shallow, it is 0, so they assigned a score of 3, but in the deep well, it has at relatively, there is 1 milligram per liter, right, I believe these units are in 1 milligram per liter, right, the milligram per liter, pardon me, and that is why they assigned a score of 0 for dissolved oxygen in this particular deep source, right. So keep that in mind. And nitrate, again a competing electron acceptor, right. So here the criteria was that it had to be for dissolved oxygen less than 0.5, but in the deep well it was greater than 0.5, that is why they assigned a score of 0. For nitrate, it has to be less than 1. So here it is 0.4, they assigned a score of 2, it was 1, again they assigned a score of 2. Again there are charts, let us say, based from historical evidence, let us say, which you can use or which people use to come up with this scoring, let us say, right. So iron, which is your electron donor, right, reducing agent, needs to be present at relatively high concentrations. So it is present at relatively high concentrations, and that is why they assigned a greater score than compared to here. I guess above a particular value they are fine with any particular concentration, but as you see in this shallow well you have greater iron, and the deep well you have lesser iron content, I guess. So sulfate, again another competing electron acceptor, so it should be less than 20, but based on the thresholds you can understand the relative importance of not importance, let us say, or relative weightage, let us say, if I can say so, of given to the competing electron acceptors, which are dissolved oxygen and nitrates, as in the dissolved oxygen has to be less than 0.5 milligram per liter, nitrate they are okay if it is less than 1 milligram per liter, and sulfate though can be low, can be as high as up to 20 milligram per liter. So in shallow it's less than 5, they gave 2. So here it's less than 1, again they gave a score of 2, right. So that's one particular case. Sulfide again, which is a reducing agent, which is an electron donor, you would want it at higher concentrations. So greater than 1 but not present at higher concentrations. This is something we saw as consistent with the other data that we looked at earlier. So that's why a score of 0. Again low concentration, that's why a score of 0. So methane, let's say, right, depending upon site, let's say it can act as electron donor, and here it should be greater than 0.5, no data, so 0, 4, so that's why they gave a higher score here, right, for the deep well, let's say. So ORP, obviously it should be reducing conditions, less than 50 or minus 100, so it's minus 58, so they gave 1, and here they have no data for the deep well, so 0 here. So pH, right, different criteria, so 6.4 they gave no score, 6.8 no score, let's say, I guess, right. So temperature greater than 20, so 22.3 and 1, so no data, 0. Obviously what role does temperature play? The greater the temperature, or until a threshold anyway, the greater the microbial activity or the greater the rate of your reactions, and thus the faster the degradation, right. So thus typically temperature they would want to be relatively higher. Carbon dioxide, it seems they want it to be 2 times and they have no data, so thus a score of 0. Alkalinity again, right, and here 9.90, 38.2, so on. Chloride again, right, so 87 they gave some scores. Volatile fatty acids, we can skip some of these aspects. And now let us move on to the relevant contaminants here. Until now we have looked at the geochemical indicators, right. All these aspects that we have looked at until now were indicators. Now let us look at the actual contaminants here, let us say, right. So these are my contaminants from out here, right. So let us look at them. So as I will just pay attention to those that were not present in the NaPl source, let us say, which are, let us say, CIS cis 1 to DCE and 1 DCE, right, and also chloroethene, ethene and ethane, right, and so on and so forth. Again based on them they were given different what do we say scores here, I guess, right. Here it is at relatively low concentration, that is why they are 0, but in this deep well they have it at relatively higher concentrations, and that is why they gave some scores. So based on this we can total it up and see that different scores were given both for the shallow and for the deep wells, right. So let us move on. Obviously this is just a summary of what I have been speaking until now, so I will skip this. You want your competing electron acceptors to be at relatively low concentrations, and you want your reducing agents or electron donors to be at relatively high concentrations, right, and the criteria that were looked at, right, and then we have a score or points that were given, and these are other sets of wells. We will just skip through this. We will just skip through this again, different sets of wells again here at different wells here again, right, and again different scores here. We now have different scores. So in this manner they evaluated all the different monitoring wells that they looked at. For just for summary, they had different obviously levels of bioremediation, let us say, that would be feasible here, let us say, right, different feasibility levels for bioremediation, right. So let us move further. So it seems they typically look at a 6-step method, so it is typically logical, as we will see. Obviously what are we going to look at? We are going to look at analyzing the relevant data, right. So available data along core of the plume, obviously core of the plume initially, right, we do not want to put in a lot of resources to determine if biodegradation is occurring, right. Then we look at, is biodegradation occurring? If it is not occurring, we look at, is it because there is no data available or data is available? We say that data is available, but biodegradation is not occurring. Then what will we do? As we talked about, engineered remediation might be required, as an engineered species might to be introduced, right, or there are other aspects that you can use, let us say, to promote biodegradation. So those aspects need to be looked at, let us say, engineered remediation. If it is because of lack of data, then I need to go back to collect screening data and then come back out here. So again, if biodegradation is occurring though, if the data suggests that, as we have seen until now, that biodegradation is occurring, what do? We locate the sources, or put in more resources and locate the sources and potential points of exposure, estimate the extent of just the NaPl residual NaPl and the one dissolved, let us say, are in the free phase, let us say, right, extent of NaPl, residual and free phase. And then moving on, we will then look at groundwater flow, and here as you can see, this is biodegradation assessment and this is fate and transport assessment. Initially we will just try to see, okay, is it feasible and is it occurring, or is there enough evidence to say that it is occurring, and then we look at, obviously we need to look at monitoring it, right, or we need to monitor this plume. So we need to look at the fate and transport of these particular contaminants. So that is the next step. So here we identified the different contaminants. Here we look at what are the factors that are going to affect the transport. Here we look at, let us say, the rate at which or the kinetics of your biodegradation, right, and then we are going to look at both the transport and attenuation models, let us say, right, and then we compare or look at all this data to see is screening criteria met. If not, go back either to engineer remediation or repeat the process with more data, or if it is feasible, so then we put in more resources for detailed natural attenuation feasibility analysis, right. So again it is pretty logical, as in we look at data to see if biodegradation is occurring. If not, look at other aspects. If it is occurring, then look at the fate and transport of the relevant contaminants, right. So again this is all at the initial stage itself, right. So let us move on. So conceptual model for contaminant transport for this site, let us look at what they came up with, right. So this is what they came up with. So transport via alluvium, right, this is something, again alluvium, as you witnessed, or we looked at the data, let us say, has this particular zone had remarkably high hydraulic conductivity, that is something to keep in mind, and also slow seepage, it seems, across the interface here, let us see, right, that is something to keep in mind. So that is their model here. And again we are going to look at the source location and transport paths. We already looked at source location in some detail, but let us look at some of the transport paths, let us say. So here they are obviously saying that it is going to flow in this direction, horizontal path. Obviously as you can see, it mirrors the path of the flow of the groundwater. Obviously it is the aquifer or this groundwater is going to move in such a way such that it is going to recharge the relevant river, right. Obviously the river is going to be recharged from the groundwater, and that is what you see out here. Again think of any river, it is going to be a relatively low lying area compared to the relevant locations around it or the surrounding area, right. So obviously horizontal flow path is one, and obviously another aspect is the vertical transport path. And why is that? Because we have DNAPL, right. So obviously this is the generic transport conceptual model, right. So two aspects, horizontal path, transport path, and vertical transport path. Horizontal transport path can lead to contamination of the river too, that is something that you see out here, right. And as you can see, the source is somewhere out here, and DNAPL, it is going to permeate through. So let us move on. So contaminant transport velocity. So obviously to estimate this contaminant transport velocity, what do you need, right? We typically try to estimate the hydraulic conductivity and the slope of this gradient, or the energy gradient is something that we need to estimate. Why is that? Because to get the Darcy's velocity, it is equal to Ki, right. So you need the hydraulic conductivity and the gradient, right, and let us see what we have. So they looked at two wells, right, and head difference was looked at, right. So hydraulic gradient was calculated, and also conductivity was measured, and then they came up with the horizontal transport velocity to be 0.05 feet per day for alluvium, anyway, for this particular alluvium, right. So let us move on. Again, what is the key aspect? K, hydraulic conductivity and the gradient, right. And let us look at the wells that were looked at in this context. So they looked at this particular well and this particular well, and looks like they are 800 feet apart, and these were the wells that they looked at to look at this or estimate this Darcy's velocity, right. So moving on, let us look at the head difference here. So hydraulic head at this different during different months, right, we have these values. Hydraulic head at the different well at different months, again we have these values, but these are just numbers, they do not make obviously much sense. So but if I look at the hydraulic head difference, as you see it varies, right, it is not constant now. So what is the key aspect here? The key aspect is that we are near the river now, right. So during monsoon, let us say, the river is going to act as a source of water, let us say, and the groundwater is going to be recharged, right, or the flow is going to be from the river towards this particular what do we say, aquifer, right? And during non-monsoon period, the flow is going to be from this aquifer into the river, right? So thus you see the difference in heads, especially during, let's say, the different months, let's say, right? So that let's try to look at the next figure where it should be more apparent. So here we have, let's say, the groundwater level on the y-axis, and with 1 year monitoring. So in the deep clay layer or in the clay layer, typically the relevant variation in the relevant what do we say now, if not deep clay layer, in the clay layer obviously, which is relatively far away from the river, you see that the groundwater level is relatively constant now, right? But in the layers which are near the relevant river, this is the profile for the river. Let's just try to highlight that. This is the profile for the river now, right? So in those layers near the river, let's say, which are silt and alluvium, right? You let's say silt, triangular, let's say, and most importantly alluvium, right? And even this 400 feet aquifer, let's say, right? What do you see? You see that their profiles, let's say, are the groundwater levels in these what do we say, aquifers or soils that are present near the river, let's say, are obviously greatly influenced by the profile or the groundwater profile of this particular river now, right? So during non-monsoon regions, the flow will be from these particular what do we say, from this particular aquifer into the river, and during the monsoon period it will be from the river into the relevant locations, let's say, right? So that's something to keep in mind. Yes. And why is that? Because with different heads, the groundwater flow direction is changing, and thus the contaminant will flow or be transported in the other direction. So that's something to keep in mind, the seasonal variations anyway. So vertical transport too, similarly they looked at two particular wells, right? And it seems 400 feet aquifer well, and they looked at hydraulic conductivity, let's say, and porosity, and then calculated the vertical transport velocity to be so on. Obviously compared to the horizontal transport velocity, the vertical transport velocity is relatively or much lesser though, right? So which wells have they looked at? They looked at these two wells to calculate the vertical transport velocity. Let's move on. So we have obviously retardation and biodegradation rate parameters to calculate, right? So in our examples, how have we done that? We have, let's say, R we can calculate by, I believe, 1 plus rho B, or dry bulk density of the soil, Kp partitioning coefficient by the porosity, right? This is how we calculate that. Again, what does retardation coefficient give you an idea about, let's say, right? In this context, we can get an idea about the total mass of the contaminant by mass present in the relevant water, let's say, right? So obviously that gives you an idea about the complexity of the system and such, right? And rate parameters by fitting the data or the fitting the model based on your mass balance to the relevant data, you can get your relevant degradation rate parameters. Let's look at what they are. So before we go there, let's say here we are looking at the partitioning coefficient. We looked at it as Kp. Obviously partitioning coefficient is going to be dependent upon the octanol water partitioning coefficient. So what is this octanol water partitioning coefficient? To refresh your memory, right? If you have octanol and water in the same container, let's say, and I introduce the relevant contaminant or the compound, I want to see, let's say, or I can measure, in which phase is it, is it present at what concentrations, right? So as in octanol, if I see that, after equilibrium has been reached, if the contaminant is present mostly in octanol, I would say it's relatively more hydrophobic, let's say, right? So it gives you an idea about the partitioning, let's say. Why is that important? Because in soil you have the organic carbon, and let's say if you have this hydrophobic compound, rather than staying in the water, it will want to be adsorbed onto this particular soil now. So that's why we also need to look at the fraction of organic carbon in the soil, right? So that's what we have here. Looks like for this site they use this empirical formula, right, which seems to be better at estimating the partitioning coefficient in terms of the octanol water partitioning coefficient and fraction of the organic carbon, right? So that's something to keep in mind. Yes. And now let's see what we have for different compounds, source compounds, right? We have different log KOW values. Keep in mind that these are log KOW values. Why is that? Because that means that this value is, or KOW value is, the KOW value is 10 to the power of 2.39, right, or greater than 100. What does that mean? So concentration of the compound in octanol by concentration of the compound in water is something like or greater than 100:1, right? What does that mean? The compound strongly wants to or is strongly hydrophobic, right? That is something that you can see out here for almost all of these compounds, right? And then they calculated the partitioning coefficient, and here we have the relevant formula out here, or the empirical formula that they observed for this. So, this is the partitioning coefficient here, right, liters per kg of soil, I believe. And here retardation coefficient, something that we looked at in our examples too, it is R equal to 1 plus rho b into Kp by porosity here. So, as you can see here, typically retardation coefficient is relatively high, and what does that tell you? Most of it is adsorbed onto the, or considerable fraction of it is adsorbed onto the relevant soil rather than being dissolved in water, right. As you can see, what does this tell you? That it is 6.5 6, as in the ratio of the total contaminant to the contaminant in the water is 6.5, right. So, that tells you that most of it is not present in the water, let us say. But again, keep in mind here the way that they calculated the retardation coefficient, they have not taken into account just the free NaPl. So, if you consider the free NaPl or NaPl present as itself, then the retardation coefficient will be remarkably high, right. Here they just looked at sorption and the NaPl present in the water. That is something to keep in mind, right. So, let us move on. So, here they looked at fractional percentage conversion for chlorinated ethanes and chlorinated ethenes, right. So, this is more or less based on stoichiometry and the relevant estimations. So, different yields, let us say, right. So, why is this relevant now, or why is this required? Because later on, let us say, not later on, when we look at the relevant data and try to analyze the system, we need to obviously understand, let this, so the sources of different compounds and how much of the compound is going to be yield, or end up being degraded for 1 mole of the source compound, right. So, in that context, obviously we need such data, right. So, again we can fit the relevant models and to the data and get the different rate coefficients, right. And I think they might have fitted it for the pseudo first order rate coefficients, if I am not wrong here, right. They gave, or even based on historical evidence, let us say, you can get these values, but typically obviously the best way would be to fit your model to the relevant data and get the relevant constants, right. You got the relevant constants. As you can see, Vc to ethene degradation is taking considerable time, maybe that is the rate limiting step. What is the rate limiting step now? How can you identify that? The one where, let us say, your reactants are building up now, as in if you need to go from A to Z, let us say all the other steps are pretty fast enough, but let us say P to Q, right, is not fast enough, right. So, you are going to observe a build up there. So, that is your rate limiting step, and looks like here, looks like anyway from this generic data that Vc to ethene is your rate limiting step, let us say, right. So, let us move on. So, here contaminant concentrations near this source zone, right, near this source zone. So, measured values and estimated values, obviously for most of the byproducts, let us say, you see that they are relatively low, right, at least initially in the source, right. That is something to keep in mind. At the source, most of these byproducts TCE, DC and VC are at relatively low concentrations, right. So, let us move on. So, here again let us look at the pathway, which is obviously the anaerobic pathway, right, based upon your particular degradation for chlorinated ethane and ethenes. Let us look at what we have, and this might seem familiar to you because I believe we looked at one of these pathways, as in PCE going to TCE and 1 to DCE vinyl chloride, and then further to further degradation, let us say, right. So, here let us say the pathway is hydrogenolysis, that is something that we observed, or we looked at earlier too, hydrogenolysis, and in other cases we have dehydrochlorination and dichloroelimination. We looked at this particular pathway and also hydrogenolysis, and we have also looks like a transformation in this case, right, from 1,1,2,2 TCE, TECA to TCE, right, trichloroethene, right, and what else. So, again, what is the take home message here? That let us say if I have these source products, right, and then I observe that my byproducts, as I can see here, like 1,2 DCE or 1,2 DCA or Ca or Vc or vinyl chloride are at relatively higher concentrations downstream, let us say, what does that tell you? That microbial activity is being able to is leading to degradation of your relevant contaminants, right. So, that is something we are going to try to look at. So, let us try to look at that data. So, let us say we have at some particular well here and some other well here, we will look at those again. We are trying to identify 1,2 DCE, cis 1,2 DCE, that is out here. As you see, the concentrations downstream in these wells are remarkably high, as we looked at earlier, they were not present in the source, right? And even vinyl chloride, as you can see, is remarkably at high concentrations, right? That's something that we can observe out here. What were the other compounds we were trying to look at? 1,2-DCA and Ca, right? 1,2-DCA, I think that's out here, right? 1,2-DCA, right? So from here you can see that, you know, your particular there is degradation taking place, and the only way it can be is due to natural attenuation, let's say, right? So that's some particular aspect to keep in mind here, right? So for example, let's say vinyl chloride, which as we saw is a byproduct, let's say was measured at, you know, this particular concentration at these two wells, let's say remarkably high concentrations, these are in milligram per liter, but if you look at it in the source, it should only be present at 0.9 milligram per liter. So as you see, it increased from 0.9 milligram per liter in the source to either 25 or 60 milligram per liter downstream, and that's only because of the biological degradation, right, or natural attenuation. So high VC concentrations were observed, and let's look at the wells where we looked at them, right? These are the wells where these are the two wells where we you know, for which we looked at the relevant data, right? And this is the source obviously, and as we saw earlier, we had horizontal transport in this direction, and at this location, let's say a few feet downstream, we see that there is considerable degradation, let's say, right? So I guess with that I'm done for today. Again, we have seen, or we, you know, the relevant aspects with respect to this case study, and also the complexity of this particular system, right? So I guess with that I'll end today's session, and thank you.